As our third example, we're going to look at a non-conducting solid sphere where the charge density is not constant. It's not evenly distributed throughout this sphere. Now, we're not going to look at the electric field outside of this shell because it's just going to come up with the same value as the last problems, because all of the Q, the charge, is going to be enclosed inside of the Gaussian shell. We already know what that's going to look like. We're interested in how do we come up with the electric field inside of this sphere. Well, the electric charge density is given by alpha r squared. So in effect, there are these rings of equal charge density around the center. So all of these are equal values of charge. It's in these concentric circles. And that's alpha r squared. So let's take a Gaussian shell inside, and its radius is going to be r. The first thing I need to do is calculate alpha. I can calculate alpha. It's not given to me because alpha is based on the total charge in this sphere. So I know that the total charge is Q, and that's just equal to the integral of the charge density times the differential volume. And what's the best way to integrate with a sphere? Well, that would be with the shell method. So let's take and think about this shell method. And I'm going to draw a circle representing a sphere. And you're going to have some differential shell in here. So you're going to have a surface area, and you're going to extend it a little bit. We're going to have a differential radius. And we did this problem similar already. We talked about this. So this surface is going to be the surface of a sphere, which is 4 pi r squared times dr. That gives me my differential volume is equal to the surface area of a sphere times a little bit more of the radius, differential r. So now I can write this integral, and I'm going to have alpha r squared for my charge density, and I'm going to have my differential volume, and my limits are going to be from 0 to r naught. Well, everything except r's are constant, so I can bring that out. And then my integral is going to be from 0 to r naught, and I have r squared times r squared, so I have r to the fourth dr. Now, the integral for r to the fourth is r to the fifth over 5, evaluated from r naught, or I should say from 0 to r naught. Well, I put a 0 in here, that's just 0, so that leaves me with 4 pi alpha r naught to the fifth over 5. And this is just equal to q. And now I need to solve for alpha. So I'm going to have alpha is equal to 5q divided by 4 pi r naught to the fifth. And so my density function is equal to 5q r squared over 4 pi r naught to the fifth. Now I need to get the q enclosed inside of this shell. I can't use ratios because it's not evenly distributed. I'm going to have to integrate from 0 to r at this on this time to be able to get my q enclosed. So my q enclosed is going to be equal to the integral of charge density times differential volume from 0 to r. Put in for my charge density. And my differential volume. And this is just going to simplify to, let's see here. You notice that the 4 pi's are going to cancel out. And then I want to keep the 5 in here. So q and epsilon naught are going to come out because they're constants. And I'll have the integral. Oh, and I put an epsilon naught in here that I didn't need to. Apologize. Did I put it in? No, I didn't. Okay, I just made that mistake there. So that means that this epsilon naught's going to go away. Oh, I wrote it again. So it's r naught to the fifth. There we go. Okay. And then my integral from 0 to r, 5r to the fourth dr. And the integral of 5r to the fourth is just r to the fifth. So that leaves me with q over r naught to the fifth, r to the fifth from R to, or from 0 to R, and that just gives me Q times R to the fifth over R naught to the fifth. That's my Q enclosed. Now I can use Gauss's law. So I'll have surface integral electric field dot dA vector is equal to Q enclosed over epsilon naught. Remember that this is symmetry. The charge density is in concentric circles. We have symmetry. That means that our electric field is going to be evenly distributed around the shell. So my E field magnitude times the integral of my differential area is equal to Q R to the fifth over epsilon naught R naught to the fifth. My integral of the surface area for the Gaussian shell is going to be 4 pi r squared and now I can simplify the r squared is going to take out the r squared from the top, and this will simplify to q r cubed over 4 pi epsilon naught r naught to the fifth. It's not squared, it's to the fifth. So that is I'm going to write this as a function of r so we remember what we're actually calculating. So the electric field is a function of r is equal to q times r cubed divided by the quantity 4 pi epsilon naught r naught to the fifth. So the important point in this problem is that we needed to calculate alpha before we started in. Alpha was very important because it helped us to simplify some of the expressions down as we got to our answer, and the answer does not depend on alpha.